Seibers. He is going to talk about chemical functionalized reduced graphite oxide as additive in polyethylene composite for radiation shielded applications. Wow, you might as well repeat that.
Well, that's okay. My name is Zach Seibers. I'm here from the Georgia Institute of Technology, and I'm excited to be here to talk a little bit about our efforts so far to develop kind of next generation radiation shielding materials that it can also maybe serve some other purposes. And so before we do that, wasn't sure the audience wanted to set up make sure we're on the same page regarding why we're doing this research, what's motivating us. We talked a lot about the risks of radiation and what we're going to have to, some of the challenges we're going to have to overcome as we move forward in our scientific or in our space endeavors. So I'm not going to talk about this a lot, but just realize that acute radiation effects can be mission halting. If they're exposed astronauts are exposed to things on the moon, that this is for a long time, within a month you can have some serious issues that would render the mission, call it early or render it a complete failure to begin with. We also are thinking about micrometeoroid impacts as well as static charge buildup with these materials that I'm going to be talking about. And so when it comes to radiation attenuation, there's generally two approaches. One is to absorb the radiation and do something chemically with that. That generally comes in the formation of radicals, ions, things of that nature. You can do some chemical reactions can occur with this. It's very useful, but it can only works for low radiation doses, certain types, and it's kind of a short-term approach for things like, if we're going to go to Mars, this isn't the best way because you do have side reactions that degrade the material in most cases. Another way we can approach this problem is to maximize the amount of hydrogen in a material or that the radiation would have to travel through. You've seen this before in pictures of nuclear reactors and things of that nature that we generally submerge in water. Liquid hydrogen is also really good. And the nice thing about this is it's already hydrogen. There's not really any way for it to degrade into anything beyond that. And so with that second concept in mind, maximizing hydrogen, when thinking about how we're going to do this, if you start exploring NASA's history with polymers and specifically radiation shielding, polyethylene comes up almost immediately. It is hands down the champion at blocking radiation per unit mass. It's very simple chemistry. It's all CH2 bonds, so if it breaks, you just end up with two smaller chains. It's not a huge issue as long as it doesn't become a point to where you're degrading all the whole carbon chain. And the problem with this generally is that it's not conductive, and although there's a range of performance tunability available to us as a material scientist, it is somewhat limited. It's just polyethylene. So to kind of tailor this a little bit to meet our needs, we're going to try and incorporate graphene. Specifically, we're going to look at reduced graphene oxides, which I'll talk a little bit more about. The whole class of graphenes, they're well known for high conductivity, excellent mechanical properties. However, if you've ever worked with them, you'll know that they're not miscible in any type of organic matrix or any bio applications. No matter what you're doing, the challenge is getting the graphene to where you want it to be. And so to this end, what our motivation is our design is to try and modify this graphene chemically such that we can retain its beneficial properties, the electrical conductivity as well as the enhanced mechanical properties, and see if we can reinforce the polyethylene matrix with these modified graphenes. And so with that idea in mind, I understand not everybody's a material scientist, so I wanted to make sure we're all on the same page here. This is just a brief cartoon explaining our process. I think I can do this. Yeah, so the first thing we're going to do is synthesize different graphene products. We're going to have a regular reduced graphene that would not feature any of these alkylation chains represented here in green, and then we're going to have the alkylated variants, which is really where the material science comes in from my perspective. Graphenes are light powder, so when working with them, you have to be careful about breathing them. So before we dump these into an extruder, just to be on the safe side, I pre-mix them in some polymer matrix. So you get this very aggregated, very heavy, intermediate product, and then we can take that and put it in it's an extruder that we put on a recirculation loop, and that will end us, hopefully, we will realize a nanocomposite with well-distributed graphene disks. So I put the slide up here hesitantly, but I wanted to show some of the successes of the survey program so far in this regard. And that is specifically, graphene oxide has been synthesized a variety of different ways. We can change the oxidation conditions. And then typically what happens is it's reduced. This product is actually water soluble. It's soluble in a lot of other solvents as well. But the point being is that we can generally process it, do things with it, and then reduce it down to graphene. And so we get this nice, conductive, mostly planar structure, but it does have a few defects remaining from this graphene oxide stage. what I'm going to do is take this product here and use it as a starting product to do this alkylation reaction, and then I'm going to reduce that further. And we can see a clear difference. This is graphite flake. This is what I start with, and this is the graphene oxide product that I would synthesize in my lab. And so with this, after we've done this synthesis, it's tricky, but we can do a few different things to confirm that we've actually successfully completed these alkylation reactions. Specifically, what I want to draw your attention to on the left here is of the IR spectrogram of the various products that I've shown so far, or that I've discussed about so far. If we look at the CC bonds, or sorry, the CH stretch, we'll see that in graphene oxide we get a nice little bump here. See if I can do this with this little pointer. But yeah, graphene oxide, we've got this nice little bump, and then when we reduce it, we get rid of all of that. And that is the change from sp3 carbon to sp2, highly planarized, and so we eliminate that CH stretch completely. In the alkylated variant, especially the graphene oxide, it's very apparent, but even in the reduced graphene oxide, we still see this little blip here. It's kind of hard to see on the graph, but there's a little bump there. You're welcome to check this out afterwards if you won't have any specific questions. And then we can also see here a couple other things, a carbonyl peak that disappears upon reduction, as well as the presence of the CO stretch here, which is indicative of the ether linkage that's connecting these alkyl chains to the graphene. Another thing we can look at is the elemental analysis. So if we look at specifically what I want to draw your attention to, I think I just clicked the wrong slide. Let's see. Okay, this carbon to oxygen ratio column here. The higher the carbon to oxygen ratio, generally speaking, the higher quality of reduced graphene you have. So reduced graphene oxide has the most carbon in the least relative to the least amount of oxygen. And then we see that upon functionalization with the alkylation agent, we see that this number goes down a little bit from 4.61 to 2.9. That's also indicative that we have these ether linkages there that have this oxygen atom in them. And so this is what we want to see. It's a good thing. That means that our chemistry has worked. So real quickly, I just want to walk you through kind of what this process looks like in the lab. We start with, this is the molten ball of polyethylene and the large aggregates you can see, they're just stuck on the outside. They're not even well incorporated. We put them into an extruder that we can do about 5 to 6 grams per batch. We mix those at 190 degrees C. We put those in a melt press, and then we get these, they're about the size of a pancake, but we get these films that, in this particular case, this is the regular reduced graphene oxide without our chemical modifications, and we can see there's clear signs of aggregation, and this is after going through all the melt processing that we're going to do with it. And then from this, we can cut whatever shape sample we want. Shown here in the bottom left, I've got three dog bone samples. The one on the left is neat high-density polyethylene, which it doesn't look like you can see very well from up here. It's blown out a little bit, but what you can hopefully see is the difference between the two samples with 0.1 weight% of reduced graphene oxide shown here. So this is the same as this pancake film. And then this is the alkylated version. So these feature the exact same amount of the reduced graphene oxide. One is just chemically modified to be more miscible. The other is unmodified and therefore is much more prone to aggregation. And so we're in the middle of doing very quantitative analysis on these samples. I've got a few things to share with you today, but what I did want to share is some kind of qualitative assessment looking at how these things are performing so far. So one of our collaborators, Valerius Apanara at UC Davis, is performing a variety of tensile measurements for us. And in these measurements, if we look at, it became quickly apparent that we were having a significant impact on the failure mode of these two very different nanocomposites. In the reduced graphene oxide, where we have a lot of aggregation, we see complete failure, which is, so it fractures. And then in the alkylated version, we see a different type of failure response, which is necking here at the, man, I don't know where I'm supposed to point this thing. But we see a necking response. So generally, this is what you think of when you think of a grocery bag, and you pull on it, it thins out, it turns white. That's actually the polyethylene crystallizing at this fracture site under as the chains reorganize. To follow this up, we can look at this, and we see that these aggregates at this interface, not only do they form, this is presumably a graphene oxide aggregate, not only do they aggregate and they're not mixing with the polyethylene, that's a problem, but they also form these voids within the polymer matrix. And this is well known in composite literature. If you look at a variety of different metal oxide type composites, they exhibit a similar failure mechanism. So a little more quantitative, we've done some DMA thermal sweeps so far, and I'm just going to show you the tan delta and the storage modulus, which is what I have here. On the left, we have reduced graphene oxide, and on the right are the composites featuring the alkylated reduced graphene oxide. And as we see here, in general, the performance is of the reduced graphene oxide is generally less than that of the alkylated reduced graphene oxide, which makes sense. That's what we would expect from this better mixing. But if we just look at, to kind of quantify how much of a difference there are, I picked out the two lines of 0.1 weight%, the same samples I showed earlier. And if we look at the alkylated version, we're seeing almost 50% increase in the storage modulus of that sample versus the unmodified reduced graphene oxide. So this is a good sign. We're having a good impact here. And something I forgot to mention is that we studied these things up to 100 degrees C. The inspiration for doing that is that replicates the environment that they would see on the lunar surface, at least on the high temperature extreme. And so to look at, finally, one of the other things that we really wanted to make sure of, as we do these, we use these materials in the moon, we want to make sure that they remain a solid, so to speak. And so one way you can analyze that is to look at the tan delta. A tan delta of way less than 1 is generally behaves like a solid, like you would expect. Something that's at 1 or greater generally becomes more of like a putty or a liquid. Think of like a rubber eraser or something of that nature. And we can see that for all the loading conditions shown that we're well below 1. And so across the thermal conditions that we tested, we are good to go for lunar applications with something like this. One of our goals in this project, as I stated, was to deal with static charge buildup. And to do that, we would have to realize a composite that was completely conductive. And so the critical result here is that I want to show is we've done some conductivity measurements on this reduced graphene oxide as well as our modified versions. And unfortunately, if we look at the column down here on the bottom right is the conductivity of these composites. And we see that there's about a factor of 1 million difference between, thank you. There's a factor of about 1 million difference, factor of about 1 million difference in conductivity between the alkylated version and the regular reduced graphene oxide. What this means is that our alkylation has compromised the integrity of the sp2 carbon plane that is generally associated with the high conductivity that we would normally see in graphene. And so with that, it's not a total failure. We thought the pinnacle challenge here was going to be to incorporate these graphenes into the polymer matrix. That was going to be the big challenge. We honestly did not believe that we could kill the conductivity with a simple reaction like this. So in conclusion, some of the points I want to drive home is that one of the things that we did that we're proud of is we've established new chemistry to efficiently functionalize these things. This reaction scheme had not been done before, and it opens up a lot of new opportunities for us to modify these graphene oxides in other ways. And I'll talk a bit more about that here in just a second. As I alluded to, we increased the miscibility with high-density polyethylene. We have so far been able to show that we've improved some of the mechanical properties. However, the conductivity is really what's hurting the performance of this composite so far, and we believe so far that that's a result of over-functionalization. And so right now, currently, I have a reaction going in the lab that is looking at some of the different ways we can modify this with different functionalizing reagents. So I used odecyl chains. Maybe we could use hexyl or something smaller. The extent of functionalization, so the amount of these chains that I graphed onto the graphene oxide. And then I can also look at the different ways there are to prepare the graphene oxide itself. So we can end up with, there are a variety of functional groups here if anybody's interested in this type of chemistry, but we can change the ratio of these, and that opens up new doors to different types of chemistry. As a preliminary attempt, we went with the one that gave us the most oxidation and the most functional groups to work with. And so we have a lot of opportunities here, we think, as well. So with that, I would like to acknowledge all the people that have made this research project possible. Of course, CERVI and then NASA with their support, but also the Reynolds Research Group shown here in this picture for putting up with me. I work on a very different type of project, lots of dirty glassware, things of that nature that they're not used to dealing with. And then I've got some people here at Georgia Tech that have really helped me along with the processing of these composites, Dr. Misha Schaffner and a couple of her students that have really come a long way in opening up their resources in their labs to our project. And so with that, I would like to take a couple minutes for any questions or comments, things of that nature.
Thank you. Any questions?
In addition to changing the chemistry, can you play with lasers or photons to do the reduction?
Yes, that's actually something we've talked a little bit about. One interesting tidbit to this research is some of this graphene oxide chemistry is new to me, and the problem is scalability, but if we were going to do it here on Earth and then ship these materials out, absolutely that's something that we're looking at. Hydrazine is the chemical we're using to do this, and it's a very protected chemical for a reason. It's extraordinarily dangerous and does have some downsides as far as synthetic applications. All right.
Thank you. Thanks very much, sir. No problem.